Hello children, now let us understand how to calculate center of mass of continuous bodies. First one is uniform straight rod. Consider a rod of length L and mass m is kept in horizontal position. Mass is uniformly distributed over the length of the rod. Its one end is taken as origin and x-axis is taken along the length of the rod. Now consider a small part of the rod whose length is dx at a distance x from one end. Mass of this small part is given by dm is equal to mass per unit length of the rod into length of this small part. So dm is equal to m by L into dx. X coordinate of center of mass is given by the formula xcm is equal to 1 by m summation of mi xi. Here in place of summation we will write integration. Xi is equal to x and mi is equal to dm, mass of this small part. So xcm is equal to 1 by m integration of x dm. dm is equal to m by L dx. M by L is constant, so it can be taken out. So xcm is equal to 1 by m into m by L integration of x dx from 0 to L. Here x varies from 0 to L. So lower limit is 0 and upper limit is L. So xcm comes out to be equal to L by 2. YCM, that is y coordinate of center of mass of the rod, is equal to 1 by m integration of y dm. Since rod is kept along the x-axis, so y will be equal to 0. So YCM is 0. So center of mass of this rod which is kept along the x-axis is equal to L by 2, 0. That is at the midpoint of this rod. Second one is calculation of center of mass of segment of a uniform circular wire. Suppose ABC is a wire which is in the shape of a circular arc. Radius of the circle is r. This arc subtends an angle 2 theta at the center. Mass of this wire is m, which is uniformly distributed over its length. We can place this wire symmetrical about x-axis and its center is at origin. Now consider a small part of this wire which makes an angle alpha with positive x-axis. This part subtends an angle d alpha at the center. From trigonometry, we know that ds is equal to r d alpha. Suppose this is equation number 1. Now we will calculate the length of this wire. We will form the logic and say that 2 pi angle is subtended at the center when length of the wire is 2 pi r. So 2 theta angle is subtended at the center when length of the wire is 2 theta into 2 pi r upon 2 pi, and that is equal to 2 r theta. So length of the wire is 2 r theta. Suppose this is equation number 2. Mass per unit length of the wire is m by L and L is equal to 2 r theta. So mass per unit length of the wire is m by 2 r theta. Mass of small part which has a length ds is given by dm is equal to mass per unit length of the wire into length of the small arc. ds is equal to r d alpha. So dm is equal to m by 2 theta into d alpha. Suppose this is equation number 3. X coordinate of center of mass of the wire is 1 by m into integration of x dm, and x is equal to r cos alpha. So xcm is equal to 1 by m integration of r cos alpha and dm is equal to m by 2 theta into d alpha. So xcm is equal to 1 by m integration of r cos alpha into m by 2 theta d alpha. Here angle alpha varies from minus theta to plus theta. So xcm comes out to be equal to r sin theta upon theta. Similarly, we can calculate YCM. YCM is equal to 1 by m integration of y dm. Y is equal to r sin alpha and alpha varies from minus theta to plus theta. So YCM comes out to be equal to 0. So center of mass of this wire is given by r sine theta upon theta comma 0. So it will be along x-axis, somewhere here. Center of mass of this wire is at bisector of this angle 2 theta. Third one is center of mass of a sector of a uniform circular plate. Suppose OABC is a sector of a uniform circular plate. Its radius is capital R and its mass is capital M. Its two endpoints A and C subtend an angle 2 theta at the center. We can place this plate symmetrical about the x-axis and its center is at origin. Now consider a small strip which is distance small r away from the center and width of this strip is dr. We can assume this strip as a sector of a thin circular wire whose x-coordinate of center of mass we have just derived as r sine theta upon theta. Suppose this is equation number 1. Let us calculate area of this sector of uniform circular plate. If this plate is complete circular plate, then its area will be pi r square. So we will form the logic and say 2 pi angle is subtended at the center when area of the plate is pi r square. So if 2 theta angle is subtended at the center, then area of the plate is equal to 2 theta into pi r square upon 2 pi, and that comes out to be equal to theta r square. Suppose this is equation number 2. Area of the strip dA is equal to theta into. We will use this equation. So dA is equal to theta into r plus dr. The dr is the width of the strip, whole square minus r square. This is in the form a square minus b square, which can be simplified as a plus b into a minus b. So after simplification, inside the bracket we get 2r dr plus dr square. Dr is very small, so dr square will be very small, which can be neglected. So dA is equal to 2 theta r dr. Suppose this is equation number 3. Let us calculate mass of the strip. Mass of the strip dm is equal to mass per unit area of the plate into area of the strip. Mass of the plate is given as capital M. Area of the plate we have calculated as theta r square. dA is equal to 2 theta r dr. So dm is equal to 2m upon capital R square into small r dr. Suppose this is equation number 4. X coordinate of center of mass of this sector of uniform circular plate is given by 1 by m integration of xcm of strip into mass of the strip. Xcm of the strip is r sine theta upon theta and mass of the strip is 2m upon capital R square into small r dr. Small r varies from 0 to capital R. So we can put these limits 0 to capital R. So xcm comes out to be equal to 2 capital R sine theta upon 3 theta. Ycm is equal to 0 because we have placed this plate symmetrical about the x-axis. So center of mass of a sector of uniform circular plate lies on the angle 2 theta bisector, that is on the x-axis in this case. Now let us see how to calculate center of mass of a composite body and center of mass of a truncated body. Suppose PQRS is a rectangular plate whose mass is m1 and center of mass is at O1. ABCD is a circular plate whose mass is m2 and center of mass is at O2. They are touching at A. We have to calculate their combined center of mass. We can assume them as 2 point masses m1 and m2 positioned at O1 and O2 respectively. So x coordinate of their combined center of mass is given by m1x1 plus m2x2 upon m1 plus m2, and y coordinate of center of mass is given by m1y1 plus m2y2 upon m1 plus m2. Suppose PQRS is a rectangular plate whose mass is m1 and center of mass is at O1. A circular hole is punched in it. We have to calculate the center of mass of this truncated body. First, we need to calculate mass and center of mass of this circular plate. Suppose mass is m2 and center of mass of this circular plate is at x2, y2. Then x coordinate of center of mass of the truncated body will be equal to m1x1 minus m2x2 upon m1 minus m2, and y coordinate of center of mass of this truncated body will be m1y1 minus m2y2 upon m1 minus m2. If a body has uniform density, then its center of mass will be located at its centroid. Let us see center of mass of some regular shapes. Center of mass of an equilateral triangle is at height h by 3 from the base, where h is height of the equilateral triangle. Center of mass of a semicircular ring is at 2r by pi from the base. We can use the formula center of mass of a sector of uniform circular ring is given by r sine theta upon theta, where 2 theta is the angle subtended at the center. Here 2 theta is equal to pi. So theta is equal to pi by 2, or center of mass is equal to 2r by pi. Center of mass of a semicircular disk is at 4r upon 3 pi. We can use the formula center of mass for a sector of uniform circular disk is given by 2r sine theta upon 3 theta. Here 2 theta is equal to pi, or theta is equal to pi by 2. So putting this value, we get center of mass is equal to 4r upon 3 pi. Center of mass of a hemispherical shell is at r by 2. Center of mass of a solid hemisphere is at 3r by 8. Center of mass of a hollow cone is at h by 3 from the base, where h is height of the cone. Center of mass of a solid cone is at h by 4 from the base, where h is height of the cone. We can prove all of these by following integration method. In the next video, we will see motion of the center of mass. If you have a question, you can ask me on my Discord server. If you have not subscribed my channel yet, please do so.